Hi, my name is Bharat Baddepudi. Today I'll be talking about building IoT and streaming applications with the latest technologies of Kafka, KSQL, and Yugabyte DB. Let's get right into it. So the agenda for seeing how we can build such application starts off with why we need reliability in streaming apps, because it's a little harder problem. We'll go through the steps of that, as well as see what solution fits into that space and what are the reasons it does, and also end off with a real world example and demo on how things fit in and how we can simulate such situations and use it effectively. So jumping right into the reliability and scalability aspects, the first, there are three top challenges. I mean, there are a lot of others, but top three challenges in streaming application is the data is coming so fast that the ingestion rate can be very high. It's like a fire hose of data coming at the infrastructure and the pieces of software that need to handle it very effectively. And then there should be no data loss. So any streaming platform, for example, guarantees that if you're going in a time-ordered series, you get the data at a given time. If you query it again, it'll be the same data point. So you need the correctness in terms of dealing with fast volume as well as being correct all the time. So there should be no loss. It should be highly reliable and performance streaming platform. So we also need to do real-time analytics. So think of a use case where you're getting information from a sensor. You want to detect it in real time that it's misbehaving or it's giving some warning about, say, high temperature, and you need to take immediate action. So those kind of ad hoc analytics have to be run on that input stream. So think of it as a moving window of latest 5 minutes. You want to see how it's performing and then respond back quickly. So there's the data stream as well as analytics running as a moving window on that data stream. So that's a almost near real-time analytics that's needed, as well as the third dimension to this problem is what do you do with the data in the data streams? One option is to write it to a database and then potentially do post-query analysis as well as do what-if analysis down the road, so that the data can be stored for longer duration as well as give insight into the near future events that are happening in the data stream that's coming in. So we need the storage to keep up with the amount of ingest, and we should be able to manage that system which is storing the data for us, and it grows. Like think of time series, and there'll be like multiple time series potentially in a real world application which come and hit the data tier. So the data tier has to keep up with such requirements. So let's see what are the well-known solutions for some of them. For ingestion into the data, we have the Kafka framework, which is has proven in the past 5 to 8 years that it's the de facto industry standard for ingesting fast volumes of data. And on top of that, they came up with the KSQL's real-time streaming analytics engine over the past couple of years, which is really thorough in giving different types of aggregations and doing modifications and transforming the data to perform the analytics on top. So these are the two de facto industry standards. And coming to the database streaming apps, what is the backend that you use for it? So that's the big question, and let's dig deeper into that aspect of the things. Right. So as I said, the database requirements to keep up with the requirements of the data stream, which guarantees the data is not lost, we need strong consistency, as in once the data is written to the database, it should be available even in case of failures, as well as at any given time, any query should give the exact value back consistently across different servers that are involved in the database. And we also spoke about the amount of data coming in increases quite a bit. So we need to have capacity planning easily that can be built on top of the database. So you should be able to do elastic scaling. So think of like a cloud model where we want the nodes to be expandable, and also the beefier machines can be added as needed. So the database needs to be able to support that kind of scaling on demand. The third aspect is highly fault tolerant. So this ties in again with not losing data. So even in case of failures, which are highly possible in a scale-out system, especially in the cloud, you don't know what aspects are failing, like disk problems, network disconnect. All those aspects have to be taken into account by the database to ensure that data is still available for the amount of failures that it guarantees. And then it also has to keep up with the speed of the ingestion rate and be able to serve as well as ingest as well as serve it for the analytics that run on it. So both write aspect and read aspect have to be very fast and also resilient to changes in the system if we do like elastic growth of the cluster, for example. So once we have performance, there is also tie-in with the amount of data, right? So you could scale to hundreds of nodes, but if each node is using like 20% of the disk, that's not really a good ROI for the end user. So each node should be able to host like terabytes of data on its like high-end SSDs or whatever requirements for the storages. So it should not waste space in terms of like using the outer layers of the disk and those SSDs or those kind of previous generation limitations. So high density is a higher requirement, one of the good requirements to have. And last but not the least, we need to be able to remove some of the data if it's not really needed. For example, maybe a week old data may not be that useful compared to like the data that's happening in the past 1 hour. And maybe 1 month old data, for example, from a sensor doesn't make sense. It's fine, we've analyzed it, reworked it, reused it, so we can expire it. So some of the next generation databases have the option to specify a TTL. That's the amount of period at which the data is automatically purged from the database, and you get better disk utilization also as a result. Now, let us tie all these three together and see how one can architect real-time insights using all the three aspects that we discussed so far: Kafka, Yugabyte database, as well as KSQL for real-time analytics. So this is a typical high-level architecture of how the devices send information to the Kafka streams that they're registered with, and the Kafka platform provides ways to send it out to the consumers who want to consume that data. For example, you can store the raw events from all the data that's coming into the database, like Yugabyte database, which is reliable, elastic, and has multi-API, and in this case, Cassandra compatible API has good aspects of TTL and some of the requirements for KSQL as well. So you can store the raw events, you can read the stream as a different consumer into KSQL for real-time analytics, and then do data modeling on top of the real-time analytics so that you can get user consumable data, which is again written back to a derived table in the Yugabyte DB. And there is like other event processing or alert notifications that can be done on top of that derived data and also displayed in real-time dashboards so that users know what is the information out there that they can use with the whole platform end-to-end, providing them insights into how the sensors and devices and other apps are performing. Cool. So just to tie it all together in terms of the Yugabyte DB requirements, what kind of solution it provides for streaming apps. So Yugabyte DB is at the intersection of NoSQL and SQL, like a next generation or third generation database, if you please. And it's also cloud native, so you can get like the elasticity features and all the time to TTL things that NoSQL provides as well. So it's a transactional planet scale database for high performance cloud services. So it provides transaction which guarantee the consistency that we talked about in a couple of slides ago. So that is what we need to be able to ingest data across different sources of streams like East Coast, West Coast on the and different geographical locations. So it is planet scale as well, tied in with the cloud native aspect for data ingestion. So here are the summary of all the things that we touched upon. Transaction also, we get multi-shard transactions across regions, you get across tables, and you get high performance, so essentially high throughput and low latency, and also the cloud native aspect. And on a side, it's also open source, so you can plug in with other open source modules and get better integration points and quicker round trip to deploying it in customer use cases. So we have the theory, and now let's do a quick information on what kind of benchmarks we have done to ensure that the data density aspect and the throughput are really useful to tie it with the 5 requirements that we talked about for the databases in the beginning. So we have done a comparison with Apache Cassandra and our own version, so we have improved. We have more 10x the density per node, so we were able to store like 26 terabyte on a 4-node cluster, and also we were able to elastically scale from 4 nodes to 5 nodes in a reasonable amount of time with the amount of data that's involved, and also able to distribute the load based on that. So that completes our information on what are the aspects that are involved in building such a system. Now let's focus on a quick real world example. So we have think of this as an industry, logistics industry case where there's a bunch of shipments going around, and the industry, the company wants to track how the shipments are doing in terms of tracking what are the types of vehicles out there, when are they reaching their destination, is there a problem with the vehicle. So we call this the CKY stack app. So we have the Confluent Kafka, we have the KSQL for processing analytics, and we have a database which takes care of tracking the data in the backend. As a quick note, this is all open source, so the app itself is on GitHub. The link is right there below. So we have the link at the bottom of the app for the app example. Just to give you the architecture of the app, like we said, there's a fleet of location tracking enabled devices like trucks or cars which are taking some amount of information, like the companies tracking them, so that when they give their location coordinates of where they are and how fast they're going, the company can predict what is the end user going to get the benefit, like the SLAs for those companies are met. So once the sensors are sending in the information, the Kafka Confluent platform will track it, and we use the Kafka Connect sync to store those into the Yugabyte database for both the raw events as well as some kind of window operations, as well as like total operations that have happened so far. So KSQL does the filtering, sends it back to the Kafka stream, and then it gets injected back into the Yugabyte DB using the Kafka Connect mechanism. And once the data is there in the database, we go ahead and display it using jQuery into the dashboard. It's a Spring Boot app which uses jQuery and WebSockets to display the output. So let's go into what are the software aspects which are needed to demo this app. So we'll start. We need a Kafka cluster to produce the data. We need the DB cluster to save the data, and the Kafka Connect, which enters the data into the database, as well as the KSQL streams and tables which do the aggregations and demo, the DDL statements for the demo. And then in the interest of time, the first 4 steps have been already done, so I'll jump into the demo. The step to be enabled is like start the actual Kafka output stream to a given Kafka stream endpoint, and then the load generator will take that and aggregate the results and put it on the UI dashboard. So let's go into the demo mode, and then after that we can see what are the things involved in the backend to make it happen, like the scripts and the commands. So I'll jump right into, so we have the Kafka producer. I just want to quickly show that we have the tables and the stream set up. For example, window traffic gives a real-time window into last 30 seconds of where the traffic, where all the fleet is, and total traffic does it from the initial time. We have a local cluster running masters and tablet servers, which is tracking the data that is coming in. So as you can see, I enabled the Kafka sync, so it's writing all the data into the database, and the 3 tablet servers, as we referred to, are saving them. And we don't see any reads because the IoT app display itself is not active yet. That's the one which reads from it and displays. So let's go ahead and start that. And then we'll come back to the Yugabyte page. So as you can see, the reads have gone up. So the display is kicking in. And this is the web page which will display all the vehicles information. Like you can see the type of vehicle, for example, on the left side, it's showing for Route 82 how many vehicles are there from the time that the app has started, as well as how many are there in the past 30 seconds. So this is the window of app that keeps automatically refreshing. And there is also trucks, how many trucks at what distance are they from a roadblock. So that will give information on any delays that are possible. So that's a quick information on how the app works in general. So let's switch back to what is involved in making this happen, and the backend, what is the secret sauce that's causing this. So now, like I said, we are taking the raw events that come from the Kafka stream, and we are ingesting it into it's published into an IoT topic. So this is what we discussed: the vehicle type, where it's at, and what speed. And then we just create a table in KSQL which has the TTL, which is highlighted at the bottom, which stores the data for like 1 hour in this case. And it also is using the Kafka Connect to convert the data from the sync, from the original topic I'm in, to the Yugabyte table for the raw. This is the raw data that is coming in. And we also have some transformations that we did on the topic itself. That's the Kafka topic, which goes into the raw events stream, as well as there is a stream we create with the information we need for different types of vehicles and their location, so that we can aggregate the data. As you can see, like it does a count over a given time interval and then sends it to a whole different table in the Yugabyte DB. And these tables are the ones we are being queried by the Spring Boot app to display. So as the data is being ingested, the data is being sent for the dashboard to do more analysis on what is happening in the system. A couple more examples of the aggregation. So we have the window traffic, which is taking like 30 seconds window, and every advance it goes by 10 seconds. So you have overlap of 20 seconds. And that is going into a different table in Cassandra query language compatible format, which does the aggregation and tracking the long-term information for that kind of traffic. And we also have the geolocation information, which is tracking how much data is, how many trucks or cars are there near a disaster point or some kind of roadblock kind of situation. And that's called the POI, the point of interest traffic, which tracks, which helps people analyze whether to do any corrective action. So that's the summary of the demo, as well as information on how to set it up. So please feel free to check out all the web pages and the documentation we have for this app. And thanks again for taking the time to listen to us. And for further information, feel free to reach out to us. Thanks again.